This is week 10 of Applied Thermodynamics course. So this week we'll look at refrigeration application or air conditioning application. So previously we saw how to use different cycles to generate power. We saw Rankine cycle, we saw internal combustion engines, which works in diesel, auto, and we saw Rankine cycle. So in this way, our focus was to generate power. But in this case, if you come to a refrigeration application, here we want to remove heat so that you will feel cold. So you just normally see your the air conditioner or your refrigerator, or you require the cooling and a lower temperature at multiple application. We know that to store food for a longer shelf life, you need at lower temperature, and your dairy products, ice creams, and throughout shipping, and you see low temperature and refrigeration application, you can see it everywhere. So here the main idea is to generate cold or a lower temperature. So in this case, we know from our second law that we cannot directly remove heat, just like we cannot convert whole amount of heat to work. Here too we cannot transfer heat from a lower temperature to higher temperature. So for that we have to give some work. So that is the main idea. So in the Carnot cycle, from lower temperature to higher temperature, you put in some work and you transfer some heat from lower temperature to higher temperature. So that is the basic idea stated by the second law. And just like how any cycle has a maximum efficiency in a power generating cycle, the Carnot engine, here too, when we run the Carnot engine in reverse, what we get is, instead of like in Carnot engine which generates power, here we put in work and you transfer heat. So that's what I mean in reverse. So if you run it in a Carnot engine in reverse, that gives you maximum performance. So that is called the coefficient of performance. That is larger for a Carnot refrigerator or a Carnot refrigerator. And other application where this is used is as an heat pump. So instead of getting this cold temperature, you need a higher temperature. So this heat pump can be used at cold temperature regions having cold temperatures. So you're feeling too cold, but you need a higher temperature. So what you do is use the heat which is getting rejected to warm up the environment which you are in, or this can be used to give in some work, but you get a better amount of heat. So this can be used in some process industries as well. So we'll see how this vapor compression refrigerators which are widely used, so how those works, and this is similar to what we saw in a Rankine cycle. So we'll see how that is similar, and then we have we saw Brayton cycle, which is a gas power cycle. So if you run that in reverse, what you get is a reverse Brayton cycle or a Joule cycle, and these are all used in aircraft engines. Joule cycle or Bell-Coleman cycle. These are different types of aircraft refrigeration systems which uses air as the medium. And there is another variant. It's called a vapor absorption refrigeration system. So we will see that also, and we will see some numericals based on VCRS and VARS. So the basic idea is we know that in a Carnot refrigerator that there are four processes which takes place in any cycle. So Carnot cycle 2, there are four processes. We know out of which there are two isothermal processes and two isentropic processes. So if we use Carnot engine, we saw that we cannot have isothermal processes. So isothermal expansion cannot take place. So that will require work to also happen and heat transfer to happen both simultaneously, which is difficult to do. So, and even here, a similar what we can do is we can bring that cycle inside the vapor pressure dome. So in that case, we can get an isothermal condition in a condenser or an evaporator. So that is possible if you bring it down into the vapor compression, into a vapor dome or a two-phase region. But the problem there again is now your compression expansion which is happening, that should happen at two-phase, which is very difficult. You cannot compress. So to modify that, what you do is you suppose this is you heat a addition in the evaporator where it picks up heat, then you need to compress it. So you cannot have it in two-phase region. So you take it out, you take such that your exit of the evaporator is at saturated condition. So your compression takes place in a single phase region. The other modification which you do is you cannot expand it in a two-phase region. If you expand it in two-phase region, initially there is a liquid and then it will flash out into vapor. So it will have difficulties in expansion. Now it's a two-phase region. So what you do is you convert that into a isenthalpic process. So initially it was an isentropic process, 3 to 4. Instead of that, what you do is you convert that to an isenthalpic process. How do you do that? You just pass it through a valve. So in this case, there is no heat transfer happening, there is no work transfer happening. So if you do a SFW, steady flow energy equation across the valve, what you get is the enthalpy which is coming in is also the enthalpy which is going out. So there is no energy loss, but there is a pressure reduction which is happening. So there is no enthalpy loss, but there is a pressure reduction. So in this case, what will happen is the enthalpy being same, your temperature will reduce. This happens because of the Joule-Thomson coefficient of the fluid. So as per when the refrigerant or a fluid which is passing through a valve, it will experience pressure reduction, and it will cause the temperature to reduce as well. So when your fluid is below the inversion temperature, you will experience a drop in temperature, and if it's greater, it will increase the temperature. So using this phenomena, this vapor compression cycle works. So your major 4 components which are in vapor compression refrigerant systems are condenser, where you will see first we'll go from compressor. So initially you have some fluid, you compress it, you take it to a higher pressure. Now if you see your compressor exit is at higher temperature. So what you do is using the ambient air, you cool the fluid. So you use a condenser to cool the fluid. So now what you will do is now the fluid is at state 2. Now you desuperate and then you condense the fluid. So hence condenser. You condense the fluid such that it will reach the saturated liquid condition, but you can also cool it some more so that it reaches subcooled condition. In that case, you will get some more latent heat in the evaporator. So after cooling in the condenser, what you do is you pass the fluid which is in liquid form to the through the expansion valve. So this will cause the fluid to expand, and then the fluid which is coming out is at a lower pressure and corresponding evaporator temperature. Now the fluid is in two-phase region. This is passed through evaporator. So now the evaporator will pick up heat where you want to cool. So from there it will absorb heat, and the fluid is boiled, and it will convert to vapor phase. So then again you pass it through the compressor. So this is the process which is happening. So now if you see, the compressor is following an isentropic process. Then in the condenser there is an isobaric process, and then in the throttle valve it's an isenthalpic process. Enthalpy is constant, and then again in the evaporator is an isobaric process. So if you see, this is similar to the Rankine cycle, except that your the expander is changed to a compressor, and then pump is now changed to expansion valve, and the process running in reverse. So there the isentropic process is converted to isenthalpic, and the compressor from the expander it was changed to compressor. But that's the idea. So here if you see, there is no because we have changed expander to throttle well, we are not getting any work here. So you are picking in some heat QL from the evaporator, then you are giving in some work, so Win, which is the work going in, and then you are losing some heat to the atmosphere. So QH is the heat. So now if you see, you need to compare how good your air conditioner or a refrigerator is. So how do you do this? You calculate COP. This is called COP, coefficient of performance. That is amount of heat which is taken in by the evaporator for per kilowatt of work which you do. So COP is defined as QL by WN, and the WN is also can be calculated based on the difference in the heat being transferred. So this is the basic idea of how a vapor compression refrigerator works. If you see, the next is a vapor absorption refrigerator. So in a vapor absorption refrigerator, the idea is used when you have a low grade of energy. So you have some amount of energy which is there, and you want to use that energy. Let it be, you can have a geothermal energy, or you want to use a solar energy, or you are in a process industry and you have some waste heat which you are dumping it in the atmosphere, but you want to make it use. So what you do is you can make use of this heat to run an refrigerator. So the idea is this heat will give you some, if you run an engine, it will give you some work. So instead of that work is used to run the compressor. So the schematic is kind of that, and what you do is you change the compressor into a system with a generator, expansion valve, absorber, and a pump. So this 4 system replaces a compressor. So what this will do is, it will the pump, if you see, the pump will take in very small amount of work compared to the compressors, because the pump here the what is pumped is a solution. So your specific volume will be very less, and so the work done in the pump will also be very less. And what you are doing is you are taking in some amount of heat which is available with you. You are using that to in the generator. So that's the idea. Your compressor is replaced with the generator, your expansion valve, absorber, and a pump. So here you can have generally what is used is an aqua ammonia absorption system or lithium bromide water absorption system. So aqua ammonia is water and ammonia. In this case, ammonia is the refrigerant and water is your absorbent. So because water absorbs ammonia, and that will form a solution. So and again other is a lithium bromide and a water absorption system. In that case, water is your refrigerant and lithium bromide is your absorbent. The lithium bromide water absorption system, a limitation is you cannot go to a lower temperature, because then water crystals may form and you cannot use that. So how this works, you have a evaporator, so where you pick up heat and then it goes, the refrigerant get absorbed in the absorber to the absorbent, and they form a solution. Now this is a diluted solution because initially assume that is water, absorber is water and ammonia. So ammonia comes and mixes with water and forms a solution. So this solution is dilute because water was rich, now it's mixed with ammonia. Now this solution is pumped through the pump to the generator. Now you have excess amount of heat lying with you. that you use that heat to make the refrigerant boil off. So ammonia is separated from water here. So ammonia is then taken to the condenser, and the water which was there, now it's or the absorbent is a now concentrated absorbent, and it's brought back to the absorber through a expansion valve. The expansion valve is required because you are pumping in, and there's a change in pressure. There's a pressure difference. So hence you are bringing in the absorbent again back through expansion valve. So this is the general idea of how the vapor absorption refrigerant system works. This is mostly very useful when you have your low grade heat which is available with you. So you are using just a small amount of work to run the pump. So we'll see some numericals how to solve VCRS and VRS. We'll start with some MCQs. So starting with, in a vapor compression refrigeration system, which component experiences the lowest temperature? So the lowest temperature is experienced by evaporator, because the exit of the valve is where the lowest temperature is. So that is in the evaporator. So the lowest temperature is experienced by evaporator, and the highest will be by condenser. So compressor exit, which you are in the superheated region, that will be the highest temperature, and that goes to the condenser. So the lowest will be in the evaporator. So the next question is, centrifugal compressors are preferred for low evaporator pressure and refrigerants with large specific volumes at lower pressure. So basically, centrifugal compressors are used when it is for large specific volumes and lower pressures. The statement is true. So centrifugal compressors are preferred for low operating pressures and compressors with large specific volumes. So the next question is, in a refrigeration system, the expansion device is connected between the dash: A, compressor and condenser; B, compressor and evaporator; C, condenser and evaporator; D, none of these. So we have seen how vapor compression refrigeration looks. So vapor compression refrigeration looks, and the components, how it's connected. So there is compressor, and then comes condenser, then comes expansion valve, and then the evaporator, which is connected to the compressor again. So now the expansion device is hence connected between the condenser and the evaporator. Hence answer C. So moving on, in a vapor absorption refrigeration system, the compressor of the vapor compression system is replaced by dash. So A, liquid pump; B, generator; C, absorber; D, absorber, generator and liquid pump. So the answer is, we have see how vapor absorption refrigeration system is different from vapor compression refrigeration system. So the answer is, we know, answer D, absorber, generator, liquid pump, and also an expansion valve, additional expansion valve, which also will be required. So this is what is used to replace the initial compressor which is used in the vapor compression refrigeration system. So the next is a gas refrigeration cycle works on the principle of dash: A, Carnot cycle; Atkinson cycle; C, Joule cycle; D, Rankine cycle. So we have seen how this works. So gas refrigeration cycle, as I told, it works in a reverse pattern, or it's also called as a Joule cycle. So it works on Joule cycle. The next is an absorption refrigeration system normally uses the refrigerant. So absorption, we use ammonia, so the answer is ammonia. So absorption refrigeration system normally uses the refrigerant ammonia. We have also seen example where absorbent, for if you use ammonia, the absorbent is water. So moving on, a refrigeration system operates on a reversed Carnot cycle. The temperature in the condenser coil is 27 degrees Celsius and that in the evaporator coil is minus 23 degrees Celsius. For a work input of 1 kilowatt, the heat received from the low temperature reservoir is dash. So basically what we need to find out is the cooling capacity. So the evaporator, how much heat it can pick up, is also called as the capacity of the system, cooling capacity of the system. So here the Carnot cycle is operating between two temperatures, which is 27 degrees Celsius, which is the hot reservoir, and the cold reservoir is at minus 23 degrees Celsius, and you are supplying 1 kilowatt of work to the Carnot cycle, reverse Carnot cycle. So in this case we need to find out the heat transferred in the low temperature reservoir. So it's pretty simple. So we know evaporator temperature minus 23 and condenser temperature 27. So and evaporator temperature in terms of Kelvin will be 273 minus 23 will come out to be 250. So now for a refrigeration system, a reverse Carnot cycle is defined as Q1 by Q2 minus Q1, and you can replace Q by temperatures in a Carnot cycle based on Kelvin's laws, and then so T1 by T2 minus T1, we are substituting temperatures here, and this will be equals to Q1 by W, the COP, and we know W, work how much we are giving in 1 kilowatt. So COP will be 250 by difference in temperature 27 minus of 23. So this will come out to be 5. So COP is 5, as we are giving in 1 kilowatt of work. The heat picked up by the evaporator will also be 5. So the heat received from low temperature reservoir is 5 kilowatt. So to the next question, a cold storage is to be maintained at minus 5 degrees Celsius while the surrounding are at 35 degrees Celsius. So again two temperature levels, minus 5 and 35 degrees Celsius. The heat leakage from the surrounding into the cold storage is estimated to be 29 kilowatt. The actual COP of the refrigeration plant is 1/3 of an ideal plant working between the same temperature. The power in kilowatt required to drive the plant is dash. So let's see how to solve this. So we know the two temperature levels, minus 5 and 35. So correspondingly the temperatures are 268 Kelvin and 308 Kelvin. Now the heat leakage coming in is what the heat load of the system. So it's 29 kilowatt. So this is additional this thing for which you have to run the system continuously. So 29 kilowatts. So now the actual COP is 1/3 of the ideal COP. So ideal COP is nothing but the Carnot cycle. So if Carnot cycle COP will then be T1 by T2 minus T1. So substituting the temperature is 268 by the difference in temperature, which is 40. So it will come out to be ideal COP 6.7. Now actual COP is 1/3 of the ideal COP. So 1/3 of 6.7 is 2.233 233 is the actual COP. Now this is equal to the heat supplied to the evaporator divided by the work supplied to the refrigerator. So 2.233 equals 29 by W. So hence the power or work which is done on the plant is 12.987, 29 by 2.233, which is close to 13 kilowatts. Hence the power required to drive the plant in this condition case is 13 kilowatt. The next question is regarding a vapor absorption refrigerant system. So the operating temperature of a single stage VARS for different components are as follows: generator at 80 degrees Celsius, your condenser and absorber are at 35 degrees Celsius, evaporator is at 0 degrees Celsius, and if the pump work is negligible, then the ideal COP of the system is dash. So in this case, the ideal COP of the refrigerator can be defined as you can think this as a show schematic. Yeah, think of this as a reversible heat engine, which is the generator absorber combination, which is driving the refrigerator. So, and here the generator is the what amount of heat which you are giving in. So this is like an engine which is producing some work to drive the reversible refrigerator. So if you see, this is an Carnot cycle. So your refrigeration is 1 minus Tg by T absorber, and COP of this is nothing but TL, lower temperature, by difference in temperature, T0 minus TL. So that's what is expressed here. So Tg minus Tc by Tg is the efficiency of the Carnot cycle running between the generator temperature and the absorber temperature. So this is 1 minus Tc by Tg and into COP of the refrigerator. So efficiency of Carnot cycle into COP of the refrigerator, of the Carnot cycle refrigerator, that will give the ideal COP of the VARS system. So now substituting the temperatures here, we will get the COP of the VARS as 0.994. So the answer is option A, 0.99. So the next question is, during the throttling expansion process in the vapor compression refrigeration system, specific volume remains same. So the answer is false, it will not remain same. So we know when the fluid is passing through an expansion valve, initially at the entrance of the expansion valve was ideal case, it is saturated liquid. So initially it was all liquid, so your specific volume will be very small. Then when it expands through the valve, at the exit of the valve is your liquid plus vapor combination. You know the specific volume of vapor is very large. So if some x fraction of vapor is formed, then at the exit of the expansion valve, your specific volume will be x fraction of vapor into specific volume of vapor plus 1 minus x into specific volume of liquid. So if you assume there is no much change in liquid specific volume, your vapor volume is very large. So your specific volume will be very large. So hence specific volume will be at the exit will be greater than your specific volume at the inlet. So hence this statement is not true, it is false. So next we will see some numericals on vapor compression system. So here it says that a reversed Carnot cycle air conditioner of 1 ton refrigeration capacity operates with a cooling coil temperature of 5 degrees Celsius, the surrounding air at 43 degrees Celsius. So your ambient temperature is 43 degrees Celsius and your evaporator temperature is 5 degrees Celsius, that's what it says, and it is used to cool the medium rising the surrounding temperature, cooling medium rising to temperature of 53 degrees Celsius. So 53 degrees Celsius is the condenser temperature. The temperature of heat rejection is, sorry, in the condenser the air is coming in at 43 degrees Celsius and it's going out 53 at 53 degrees Celsius, and your condenser temperature is at 55 degrees Celsius. Okay, so the overall heat transfer coefficient of the heat exchanger between the working substance and the surrounding air is 250 watt per meter square Kelvin. So heat transfer coefficient is given, overall heat transfer coefficient. Then determine the mass flow rate of the surrounding air entering the heat exchanger, area of the heat exchanger, COP, and power consumption of the air conditioner. So this is the first part of the question. So we'll solve this and we'll come back again for part B. So initially we know that in a refrigerator, so I'll show you. So this is the vapor compression refrigeration system. So in condenser, this is operating at 55 degrees Celsius. To cool this condenser, you are using ambient air. So ambient air that is coming into the condenser at 43 degrees Celsius, and there is a rise of 10 degrees Celsius of the air, and it's going out at 53 degrees Celsius. So that's what is happening in the condenser, and the condenser is at 55 degrees Celsius. Here 3 is 55. And your evaporator temperature is at 5 degrees Celsius. So for this, if you run an Carnot cycle between this temperatures, that is 55 and 5 degrees Celsius, you will have a COP of 5.56. So that was asked COP. So we have found out the COP. COP will be 5.56. Now next is this is the ideal COP, maximum COP which you can get. Now the power consumption is nothing but the work done is Q, heat supplied to the evaporator, divided by the COP. COP is ideal COP, Carnot COP, EC is Carnot COP. So your heat is taken is 1 ton. 1 ton is nothing but 3.52 kilowatts. So you can substitute that 3.5167 divided by 5.56, the COP. So you will require 0.63 kilowatts of power. So now using this we can find out the heat which is rejected in the condenser. So the heat which is rejected in the condenser is heat which is coming in the evaporator plus the work done. So you adding this will get that heat rejected is 4.15 kilowatt. So we know amount of heat which is getting rejected. So we have found out COP, we have found out power consumption of air conditioner. So now we need to find out the mass flow rate of the cooling air. For that we know how much heat is rejected in the condenser. So Q equals to mCp delta T. So M is mass of air, so Q by Cp of air into delta T of air. So Q we know 4.15 divided by 1.005 kilojoule per kg into 53 and 43 are the temperature, so difference 10. So this will give me the mass flow rate of cooling air as 0.413 kg per second. So this is the mass of air which is flowing in the condenser. So next is we need to find out the area of the heat exchanger. So heat exchanger area can be found out using heat transfer in the heat exchanger Q is equals to UA into LMTD, logarithmic mean temperature difference. So we know here overall heat transfer coefficient as 250 watt per meter square Kelvin, and we know Q, heat which is rejected in the condenser. So only thing we have to find out is the logarithmic mean temperature. So that also we can find out. We know that in the condenser your temperature is at 55 degrees Celsius, and the fluid which is coming in is at 43 and going out is at 53. So your temperatures are temperature difference at both ends are 55 minus 53. At the hot side will be 2 degrees Celsius, and 55 minus 43 which is 12. So using that, you can find out the logarithmic mean temperature differences delta T1 minus delta T2 by ln delta T1 by delta T2. So substituting that, we can find out that mean temperature difference between the streams is 5.58 degrees Celsius. So substituting this in the equation to find out area, we get area as 2.975 meters square. So the area of heat exchanger required is close to 3 meters square of area is required in the condenser to reject 4.15 kilowatts of heat. So that was the first part of the question. Now they say if water is used instead of air, now we are using water as the cooling medium, and the water is available at 30 degrees Celsius. So now this is used in the same heat exchanger. Will its area be adequate or inadequate for necessary heat rejection? Assume that mass flow rate of water remains the same as that of air. So mass flow rate which we calculated, that remains same. Also your water your overall heat transfer is 10 times more. So now 2500 watts per meter square Kelvin. So that is B part of question. Now C part of question, they say if area is reduced to 1 meter square, what will be the temperature of heat rejection, temperature rise of water, COP power consumption, and percentage saving in power consumption and percentage reduction in the heat exchanger area as compared with air as a cooling medium. We'll see how to solve this. So now if we use water as a cooling medium, so first approximation which we make is your evaporator temperature is at 35 degrees Celsius. So now we find out the COP again. So 273 plus 5 divided by 35 minus 5. So this will come out to be 9.27. So your COP is more. Now they say heat rejected is again Q naught, which is heat taken in, plus W. So for Q of 1 ton 3.52, your Q rejected will come out to be 3.9 kilowatt. So 3.9 kilowatt of heat has to be rejected. So for this case, we find out that your delta T of water is coming out to be 2.26 degrees Celsius for same amount of water flowing similar to air. So CP is 4.186, and for 3.9 kilowatt, the rise in temperature of the water is 2.26 degrees Celsius. So your inlet is at 30 degrees and the exit is at 32.26 degrees. So now if you find out the same logarithmic mean temperature difference, the difference comes out to be 3.76 degrees Celsius. So for this mean temperature, the area required is 0.41 meter square. So if you see, this is very small compared to the initial 2.975 meter square area which was required for an air cooled condenser. So now if you see, so the temperature in the condenser can be much lower. So we assumed that to be 35. So now we can bring this down again, so that we can increase the area. So now if you take the second approximation of the condenser temperature to be 33 degrees Celsius and solve similarly, we will find out that area comes out to be 0.95 meter square. So if you see, this is close to 1, which was asked in the third part of the question. So we'll see how to solve that, but before that, so the area required is still 1/4 of the available area of 2.975 meter square. So even if we take the exit temperature 32.24 So if you take your condensate temperature equal to the exit temperature of the water, so in that case what will happen is your one side temperature difference will become 0, the other side temperature difference is 2.24, and for this the mean temperature will come out to be 1.12 degrees Celsius. So for this the area required is 1.38 meter square. So 1.38 is still very lower than compared to the air side air cooled condenser area. So hence the area which is there is more than adequate for uh, cooling, and it can be reduced to 1/3. So now we, in the previous problem we saw that when we take your condenser temperature is 33 degrees Celsius, we get area requirement of 0.95 meter square. The third part of the question, it was asked if you take area of the condenser to be 1 meter square. So with a similar iteration we can first see that condenser temperature, if we take it as 32.94 degrees Celsius, then we require area to be 1 meter square. So now using this we can find out the COP, which comes out to be 9.95, and similarly the heat rejected is 3.87 kilowatt, and delta TH is a change in water temperature is 2.24, and similarly we can find out the logarithm mean temperature and area if it comes out to be 1 meter square. Now for this the power consumption is 3.5167 divided by 9.95. 3.5167 is the heat load required or cooling capacity divided by COP, which will come out to be 0.35 kilowatt. Now if you see, this is running at 0.35. Previously we saw that the compressor work is 0.63 kilowatt. So the fraction of percentage increase in power consumption is 0.63 minus 0.35 divided by 0.63. It will come out to be 44.4. So there is a saving of 44% of power. And see, if you see saving in area of heat exchanger, previously 2.975 meter square of heat exchanger was used, minus 1 for current condition divided by 2.975. So we see 66% reduction in heat exchanger area is observed when we switch from air cooled condenser to a, it's at 43 degrees Celsius, to a water cooled condenser with which the temperature is of 30 degrees Celsius. So next is we have a R134A vapor compression engine system operating at a condenser temperature of 40 degrees Celsius and an evaporator temperature of 0 degrees Celsius. It develops 15 tons of refrigeration. So that is the cooling capacity. So using the pH diagram for R134A, determine the discharge temperature and mass flow rate of refrigerant circulated. Then the theoretical piston displacement of the compressor and piston displacement per ton of refrigeration, theoretical horsepower of the compressor and horsepower per ton of refrigeration. So specific work and work. Then heat rejected in the condenser and Carnot COP and actual COP of the cycle. So we will see how to solve this. So I'll just switch to, we'll see how to solve this. So the conditions which we know is it is condenser temperature is at 40 degrees Celsius and evaporator temperature is at 0 degrees Celsius. So this is the R134A chart. So if you see, we are operating between 0 and 40 degrees Celsius. So 0 is your evaporator temperature, and the exit of evaporator temperature you are assuming it to be a saturated vapor. So from there there is an isentropic compression which is happening. So from 0, if you follow an constant entropy lines. So constant entropy lines is this dotted lines here, which is close to horizontal, which is becoming close to horizontal. So from 0 degrees Celsius, if you follow the isentropic line, to the same pressure here. So your pressure is so this will line will meet somewhere close to 40 and between 40 and 50. Sorry, this constant entropy lines is this dot and dash line. So from 0 degrees Celsius, if you draw a line here, it will lie between this 600 and 650 line. So if you draw from 0, it will go like this, and your pressure remains constant here in the condenser. So exit pressure it will be lying somewhere here. So if you see, this temperature is lying between this 40 isothermal line of 40 degrees Celsius and isothermal line of 50 degrees Celsius. So it will lie somewhere here. So your temperature will be between 40 and 50, and from there you desuperate, and then in condenser you reach a saturated liquid condition, and then do an isenthalpic process to 0. That's how the process will look like. So now going back to the problem, from the chart we can infer that your pressure for 0 degrees Celsius is 0.2958. so this will be your evaporator pressure, and the enthalpy at evaporator exit will be 398.6, and the corresponding entropy is 1.7541. Also the specific heat capacity Cp is 1.145 kilojoule per kg Kelvin. Then at condenser condition is your pressure is 1.0166 megapascal for 40 degrees Celsius, and the specific volume at inlet is, so compressor is 0.06931 meter cube per kg. S2 dash is the compressor exit. This guy is equals to 1.711 kilojoule per kg, and H4 is the exit temperature of the expansion valve or saturated liquid evaporated saturated liquid in condenser. So that enthalpy is 256.41 kilojoule per kg. So now for isentropic compression, so S2 equals S1, so entropy will constant, so this is equals to 1.7541 plus Cp ln T2 by T1. So this is the compressor exit condenser temperature. So from this we can find out the temperature at exit of the compressor is 44.4 degree Celsius, 317.6 Kelvin, which we saw in the chart that it lies between 40 and 50. This H2 dash is the saturated vapor condition in the condenser. So we assume that we know you can either calculate directly this from the chart, or you can use the entropy balance to find out the temperature. So S2 dash will be equals to 1.7541 plus Cp ln T2 by your condenser temperature 313. So you can use the entropy calculation to find out the temperature here. So now once the temperature is found out, then we can find out H2. H2 is the enthalpy at the compressor exit. So compressor exit is vapor enthalpy plus Cp T2 minus T2 dash is the superheat temperature. So saturated vapor at the 40 degrees Celsius is 419.43 plus Cp is 1.145 into the degree of superheat is 4.4, so into 4.4. This will come out to be 4 to 4.5 kilojoule per kg. This is the enthalpy at the compressor exit. This can be calculated directly from the chart, or it's the other way of calculating if we don't have chart. So hence the work in compressor is H2 minus H1, which will come out to be 25.9 kilojoule per kg. Now the specific cooling capacity is Q0 is H1 minus H4, which will come out to be 398.6 minus 256.41, which is 142.19 kilojoule per kg. So the mass of refrigerant which is flowing in the system is the cooling capacity of the system, which is 15 ton given, divided by the specific cooling capacity. So 15 into 211 divided by 142.19. So this will come out to be 22.26 kg per minute. Next is the theoretical piston displacement of the compressor. So theoretical piston displacement is m dot into specific volume. So 22.26 is the mass flowing into specific volume is 0.06931. So this will come out to be 1.543 meter cube per minute. So that is the specific volume. So the next is specific piston displacement per ton of refrigeration. So 1.54 divided by 15. So it will come out to be 0.1029 meter cube per minute for 1 ton. So the next is to find out the work. So the total work is mass into the specific work. So that we 22.26 into change in enthalpy divided by 60, which will come out to be 9.61 kilowatt. So next is the horsepower. Question is to find out theoretical horsepower. So divide by 746 will come out to be 12.88 horsepower, and horsepower per ton is divided by 15 will come out to be 0.86 horsepower per ton. The heat rejected is similarly m dot into H2 minus H3, which will come out to be 62.36 kilowatt. and the COP can be found out using cooling capacity divided by specific volume, specific cooling capacity divided by specific work done. So 142.19 divided by 25.9 will come out to be 5.49. So that is the COP of the system. So the next question is, we have a R134A which enters the compressor of a vapor compression refrigeration cycle at 120 kilopascal as a saturated vapor and leaves at 90 kilopascal, 900 kilopascal and 75 degrees Celsius. The refrigerant leaves the condenser as a saturated liquid. So condenser exit is saturated liquid. The rate of cooling provided by the system is 18,000 BTU per hour. BTU is British thermal unit. So determine the mass flow rate of R134A, the COP of the cycle. Determine the COP of the cycle if the expansion valve is replaced by an isentropic turbine. So do you recommend such replacement for refrigeration system? Then determine the COP if the evaporator is 160 kilopascal instead of 120. In the other part is determine the COP if the condenser pressure is 800 kilopascal instead of 900. So this is how the cycle will look. So 120 kilopascal and 900 kilopascal is the operating pressures. So we draw an isobars across it, and we have isentropic compression. So 3 saturated liquid, the exit of condenser. After that we do a isenthalpic expansion initially. So from the R134A chart we can find out the corresponding enthalpies. So for 120 kilopascal and saturated vapor condition, the enthalpy is 236.97 kilojoule per kg. Similarly, at 900 kilopascal and 75 degrees Celsius, the enthalpy is 310.51, and similarly saturated liquid condition enthalpy is 101.61 kilojoule per kg. And enthalpy at state 3 and enthalpy at state 4 will remain same. So now specific work done for this system is H2 minus H1, and it will come out to be 73.54 kilojoule per kg. Similarly, the heat absorbed in the evaporator is H1 minus H4, which is equal to 135.4 kilojoule per kg. So the mass flow rate of R134A in the system is, so we know that the heat which is absorbed in the evaporator is 18,000 BTU per hour. So we convert it into kilowatt. So divide by 3412.14. So 1 kilowatt is 3412.14 BTU per hour. So we divide it by that and divide by the specific heat absorbed. So that will come out to be 0.039 kg per second. So this is the mass of refrigerant which is flowing in the system. Now the COP of the system is heat absorbed QL divided by W. So 135.4 divided by 73.54, which will come out to be 1.84. So the COP is 1.84. Now the next part of the question was to replace the expansion valve with an isentropic turbine. That's done. Then we know S3 from the chart is at 0.3738. So this is the entropy. So the entropy will remain same. So in isentropic expansion, so entropy of 0.3738 and the exit pressure of 120 kilopascal, which will give me the enthalpy as 92.98 kilojoule per kg. So the work generated in the turbine is 8.363 kilojoule per kg. So the net work is 64.91 kilojoule per kg. And similarly, the specific heat absorbed is 144 kilojoule per kg. You see, this is larger than the previous one, and your work done is also lower. So now COP, if you see, COP has increased from 1.84 to 2.21. So the COP increased by 20.1% by replacing the expansion valve by turbine, This replacement makes thermodynamic sense since it decreases the work requirement and thus increases COP. However, this is not practical for household refrigerators and most other refrigerant systems. So theoretically, this is a better option, but practically, this is not possible. So the next part is when we change the evaporator pressure from 120 kilopascal to 160 kilopascal. So similarly, we can find out all the values, and if we find out all the enthalpies of the 4 points, the COP is H1 minus H4 by H2 minus H1. So this will come out to be 2.01. So increasing the evaporator pressure from 140 to 160 kilopascal increases the evaporator temperature. Initially it was operating at minus 22.3. Now increasing the evaporator pressure to 160 kilopascal changes the evaporating temperature to minus 15.6. So evaporator temperature will go up, but COP will also go up. So from 1.84 to 2.01%, so which is an increase of 9.2%. Similarly, when the condenser temperature is brought down from 900 kilopascal to 800 kilopascal, similarly if we calculate COP, it is 1.89. So decreasing condenser pressure decreases the condensing temperature from 35.5 degrees Celsius to 31.33. So condensing temperature has come down and COP is also increased, but the increase is very small, which is of 2.7%. The next question is, an ammonia ice plant operates between a condenser temperature of 35 degrees Celsius and an evaporator temperature of minus 15 degrees Celsius. It produces 10 tons ice per day from water at 30 degrees Celsius to ice at minus 5 degrees Celsius. Assuming simple saturation cycle, using only tables of properties of ammonia, determine the capacity of the refrigeration plant, the mass flow rate of refrigerant, the discharge temperature, the compressor cylinder diameter, and stroke of its stroke if its volumetric efficiency is 0.65, then speed is 1200, and stroke bore ratio is 1.2. Horsepower of the compressor motor, if the adiabatic efficiency of the compressor is 0.85 and mechanical efficiency is 0.95, then the theoretical and actual COP. So let's see how to solve this one by one. So things which we need to see is the condenser is at 35 degrees Celsius, evaporator is minus 15, and it produces 10 tons of ice. So mass of ice is 10 tons per day, and your water is brought down from 30 degrees Celsius to minus 5. So there is some sensible cooling, and then latent heat is removed, and then again sensible cooling. So this is how the ammonia refrigeration works. So there is two types of process shown: wet compression and a dry compression. So 1 to 2 isentropic process, and 2 to 3, 3 to 4 isenthalpic. 3 to 4 is isenthalpic, and then again in the evaporator where it absorbs heat. So the refrigeration capacity is 10 tons. So 10 into 1 ton is 1000 kg. So 10 into 1000 divided by per day 24 hours. So converting into hours, divide by 24 into 4.1868 is the CP of water, which is brought down from 30 to 0 degrees Celsius. From 0 degrees Celsius, there is a latent heat, which is for solidification, which is 335. Then CP of ice is 1.94 into it is brought down to 5. So into 5, 0 minus 5. So this will come out to be 195.960 kilojoule per hour. So converting into watts, it will come out to be 54.43 kilowatt. So that is the cooling capacity required. So from table of ammonia we can find out at minus 15 degrees Celsius the saturated vapor condition enthalpy is 1443.9 and your entropy is 5.8223. Similarly, your saturated liquid condition is at 35 degrees Celsius is 366.1 kilojoule per kg. So using this we can find out the specific cooling capacity, which is H1 minus H4, which will come out to be 1077.8 kilojoule per kg. So using this we can find out the mass of refrigerant, which is nothing but the cooling capacity, refrigeration capacity divided by the specific cooling capacity. So this will come out to be 181.7 kg per hour. So this is the mass of ammonia required to in the as a refrigerant. Then from the table, the entropies and enthalpies of vapor saturated at 35 degrees Celsius and superheated by 50 and 100 kelvins are respectively. So the enthalpy and entropy and enthalpy values of saturated vapor 2 dash here and 2 double dash and 2 triple dash is shown. So all entropies and enthalpies values are given here. Now as we know that your entropy is at 1 is 5.823 and this value lies between 50 Kelvin superheat and 100 Kelvin superheat, so it should lie somewhere in between. So using interpolation we can find out, and the temperature is 112.1 degrees Celsius or 77.1 degree superheat. So that is the temperature of the compressor exit. Now the next part of the question is to find out the piston displacement of the compressor. So for that it's nothing but the volume flow rate, which is given by pi by 4 d square into L, which is the volume, into n, the speed of rotation. Using this we can find out the specific volume, swept volume. So substituting the values, this will be equal to the actual volume flow rate, so m dot into specific volume divided by volumetric efficiency. So volumetric efficiency is actual volume flow rate divided by the swept volume. So this will come out to be using this, diameter is 0.128 meter and L is nothing but 1.2 times diameter, so L is 0.154 meter. So this is the piston dimensions. The cylinder dimension. Then the enthalpy of discharge by interpolation. So we know enthalpy at 2 double dash and 2 triple dash, and we know the temperature. So using interpolation we can find out the enthalpy at the exit of compressor as 1703 kilojoule per kg. Now using this we can find out the power consumption. So power consumption is m dot into h1 minus h2. So h1 we already know h1 1443.9 and h2 we have calculated. So and m dot also is known. So this is the work done in the compressor, and the compressor has adiabatic efficiency and mechanical efficiency, so 0.85 and 0.95. So dividing it by the efficiencies we'll get the actual work done. So actual work done will come out to be 16.21 kilowatt. So now converting into horsepower, we divide it by 746, which is equals to 21.73 horsepower. Now next question is to find out the COP. So COP is nothing but H1 minus H4 divided by H2 minus H1, or work done, specific work done divided by specific cooling capacity divided by specific work done, which will come out to be 4.16. Now the actual COP, this is ideal COP, sorry, theoretical COP. The actual COP is Q naught divided by W. We have calculated W, and Q naught is 54.43 kilowatt, which we have calculated. So it will come out to be 3.36 kilowatt. So moving on, we have an ammonia refrigerating machine which is working at similarly same 35 and minus 15 degrees Celsius in the evaporator. We are assuming two cases, one is dry compression and other is wet compression. Calculate for each the following: the theoretical piston displacement per ton refrigeration, the theoretical horsepower per ton refrigeration, and COP. So this is what I have shown: wet compression and dry compression. Wet compression is your end of compression is at saturated vapor, and in dry compression your inlet to compression is saturated vapor. So this is the two cases. So if you see, we have already calculated 1 and 2, so we need to calculate 1 2 dash, case for 1 2 dash. So this is the 2 which is calculated in the previous problem, so we'll use that. So refrigeration circulating rate per ton of refrigeration, which is 211 divided by 1077.8. If you see, 1077.8 is your specific cooling capacity. It will come out to be 0.1956 kg per minute of for 1 ton refrigeration. Now theoretical piston displacement per ton is m dot into V1 into 60. So similarly we have calculated a specific volume and mass flow rate in the previous problem. Sorry, we have calculated for mass flow rate here. So and so specific theoretical piston displacement is 5.975 meter cube per hour. So theoretical horsepower is m dot into work, specific work done, which is 259.4, which is H1 minus H2 minus H1 divided by divided by 60 into 746. So that will give me 1.15 horsepower per ton, and COP is a specific cooling capacity by work done. So 1078.5 divided by 259.1, which will come out to be 4.16. This is not 90, this is 60. And then we have found out the COP. COP is 4.16. Now we proceed with compression. Similarly, we can find out we know saturated vapor condition. So using entropy, we find out dryness fraction at state 1. So that will come out to be 0.88. So we know saturated liquid entropy and saturated vapor entropy, and we know the entropy at state 1. So we can find out X. Using that, we find out the enthalpy. So enthalpy will come out to be 1286.1 kilojoule per kg. Then we can also find out the specific volume. So specific volume will be 0.448 meter cube per kg. So similarly, specific cooling capacity and specific work is 920 kilojoule per kg and 202.5 kilojoule per kg. So refrigerant circulation rate is 211 by 920, which will come out to be 0.229 kg per minute ton. theoretical piston displacement per ton is similarly m dot into V. So m dot is 0.229 into specific volume is we calculated 0.448 into 60, it will come out to be 6.159. So now is to calculate the COP. So COP is theoretical horsepower. Theoretical horsepower per ton is we have calculated m dot into work, specific work done is 202. So divide by 60 into 0.736. So it will come out to be 1.05 horsepower per ton. And similarly COP is COP is 920 by 202.5. It will come out to be 4.55. So next is a similar problem with the R134A. Now instead of a refrigerator, we are using it as a heat pump for space heating. So which operates at temperatures between 15 and 50 degrees Celsius. So the heat required to be pumped is 100 megajoule per hour. So now to determine the dryness fraction of refrigerator entering the evaporator, the discharge temperature assuming the specific heat of vapor as 0.996, theoretical piston displacement of the compressor, theoretical horsepower of the compressor, and the COP. The specific volume of R134 is saturated vapor at 15 degrees Celsius is given, which is 0.04185. And so other relevant properties are, specific your specific enthalpies are given for saturated vapor and saturated liquid condition, and entropies are given, and pressures is also known. So now using this we can find out the dryness fraction. So we know enthalpy at exit of inlet of the evaporator is saturated liquid condition at 50 degrees Celsius. So that will be 271.62. So using this we can find out the dryness fraction. So enthalpy H3 will be equals to x into Hg at 15 plus 1 minus x Hf at 15. So using this we can find out the dryness fraction, which will come out to be 0.274. So now we need to find out the discharge temperature. So for finding out discharge temperature, we know the exit entropy of the compressor is the saturated vapor at 15. So which is equal to 1.072 1.72. So and we also know the entropy from saturated vapor from 50 to the exit temperature is S2 dash plus CPln T2 by T2 dash. So S2 dash is known, saturated vapor enthalpy at 50 degrees Celsius is 1.7072 plus Cp is 1.246 into Ln change in temperature T2 by 273 plus 50. We can find out temperature. This will come out to be 327.15, is 53 degrees Celsius. So now similarly enthalpy we can calculate H2 dash plus Cp T2 minus T2 dash, which will come out to be 427.2. So the mass flow rate is 10,000 megajoules. So 100 megajoules. So 100 into 10 power 3 divided by 3600. This is in kilowatts, divided by 427.2 minus 271.62, which is H2 minus H3. It will come out to be 0.179 kg per second. So now theoretical piston displacement is nothing but mass flow rate into specific volume. Specific volume is given, so m dot into specific volume will come out to be 7.539 into 10 power minus 3. Now power consumption similarly is m dot into H2 minus H1. So H2 we have found out, compressor exit minus H1 is known saturated vapor at 15. So 0.179 into change in enthalpy, it will come out to be 3.6 kilowatt. So 3.6 divided by 746, it will come out to be 4.82 horsepower. Now the heating capacity is m dot into H2 minus H3, which is rejected in the condenser. So that will come out to be 27.9 kilowatt. So the theoretical COP is, now in this case will be heat rejected in the condenser divided by the work supplied. So H2 minus H3 by H2 minus H1, which will come out to be 7.75. So alternately we can find out using values which we have calculated. So it will come out to be same. So if you see, only 3.6 kilowatt of work is supplied, and 27.9 kilowatt of heat is rejected in the heating space. If we use a simple electric heater, we'll get only 3.6 kilowatt. So now using heat pump, there's a proportion, there's a close to 8 times large heat which is supplied to the heating space. So for heating, so this is a better option using heat pump compared to an electrical heater. So now we'll see some problem on absorption refrigeration system. So consider basic ARS using ammonia water solution as shown in figure. A pure ammonia enters the condenser at 2.5 megapascal and 60 degrees Celsius at a rate of 0.022 kg per second. And ammonia leaves the condenser as a saturated liquid and is throttled to a pressure of 0.15 megapascal. So ammonia leaves the evaporator as a saturated vapor. Heat is supplied to the generator by geothermal liquid water that enters at 135 degrees Celsius. This is at a rate of 0.35 kg per second, and it leaves at 120 degrees Celsius. So this is in generator. So now determine the rate of cooling provided by the system and the COP of the system. Determine the second law efficiency of the system if the ambient temperature is 25 degrees Celsius and the temperature of the refrigerated space is 2 degrees Celsius. The enthalpies of ammonia at various states of the system are given as H31497. Take the specific, so enthalpies are given, and take the specific heat of water as to be 4.2 kilojoule per kg. So this is how the vapor absorption diffusion system is. So condenser, there is a throttling valve evaporator which is at 2 degrees and 25 degrees Celsius, and then so now ambient is at 20, this is at 60 degrees Celsius, and generator is using geothermal. So the water is coming at 135 and going at 120. So this is what is known. So the rate of cooling provided by the system is evaporator 6 minus 5. So m dot into m dot refrigerator into 6 minus 5. The refrigerator flow rate is 0.022, which is given. So ammonia enters the condenser. So this part of the loop contains only the refrigerant ammonia. 3, 4, 5, 6 was only ammonia. So the flow rate will remain same. So what is entering the condenser is also what entering the evaporator. So 0.022 into the enthalpy values which is given between 6 and 5. will come out to be 20.9 kilowatt. So this is the cooling capacity provided. And now the rate of heat input to the generator is m dot cp delta t. So m is 0.35 kg per second of water coming in, which is cp is 4.2, and water is coming in at 135 and going at 120. So 135 minus 120, it will come out to be 22.1 kilowatt of heat which is supplied to the generator. So now if you see, if we neglect that pump work done in the pump, COP is Q dot L by Qg. Q dot L is heat capacity you got in the evaporator divided by heat you are supplying. So 20.9 divided by 22.1 will come out to be 0.946. So now, in order to develop a relation for the maximum COP of an absorption refrigerator system, we consider a reversible heat engine and a reversible refrigerator as shown in figure. So now heat is absorbed by at source temperature. So the basic idea is converting this to a schematic running by reversible heat engine which is driving a reversible refrigerator, so which I explained previously. So in that case, the COP will come out to be 1 minus T naught by Ts into TL by T naught minus TL. So this is a schematic of a reversible heat engine driving a reversible refrigerator. So now substituting this the values, we'll get so here we generator, we assume it's 135 and 120. So we'll take a mean temperature for this generator source temperature, say 127.5, and we know that lower temperature is 2 degrees Celsius and 25 degrees Celsius. So on substituting here, we'll get COP is 3.06. So now the temperature of each source is taken as the average. Now the second law efficiency is nothing but COP divided by COP of the ideal cycle. So COP of ideal cycle is 3.06 and COP of the cycle is here 0.946. So the exergy efficiency is 30.9%. So this is to find out the second law efficiency. We have assumed that converting this actual system to a Carnot system with a reversible heat engine driving a reversible refrigerator. Now similarly, we'll see one more vapor compression system. So a refrigerator uses a R134A as a refrigerator. Is used to keep a space at minus 10 degrees Celsius by refrigerating heat to ambient air at 22 degrees Celsius. So it's running between minus 10 and 22. So R134A enters the compressor at 140 kilopascal at a flow rate of 375 liters per minute as a saturated vapor. The isentropic efficiency of the compressor is 80%. The refrigerant leaves the condenser at 46.3 degrees Celsius and as a saturated liquid. So determine the rate of cooling provided by the system, the COP, the exergy destruction in each component of the cycle, the second law efficiency of the cycle, and the total exergy destruction in the cycle. So this is just to do a second law analysis of the VCRS. So it's a bit complicated. So we'll see. It's not required. It's not taught a second law analysis, but even though I'm taking a problem, I'll see how to solve this. So we know mass flow rate of the refrigerant. So M is V1 by specific volume. So we know volume flow rate, which is 0.375 liters per minute. So divide by 60 and 10 power minus 3 to convert into meter cube. Divide by specific volume, it will come out to be 0.04458 kg per second. So this is the mass flow rate. Now we can calculate the refrigerant load. We can find out the enthalpies, corresponding enthalpies from the chart, R134A chart. So we can find out H1, H4, H3 and H2. H2 is isentropic H2S is isentropic case, and assuming an 80% compressor efficiency, we can find out H2. So using that, we see that enthalpies, we can, after finding out enthalpies, we can find out each of the heat and work done. So Q in the evaporator is 5.41 kilowatt, Q in the condenser is 7.92 kilowatt, and work done is 2.50 kilowatt. And the next is to find out the COP of the cycle. So COP of the cycle is QL rejected divided by WN, which is 2.16. To the right, I have shown how to solve, how to find the enthalpies and of the each of the four state points. So using R134A chart and the similar process which we have seen in the previous problems, so we can find out all the enthalpies. So now we have found out COP and work done and heat rejected. So next is to find out the exergy destroyed in each of the components. So we know ambient temperature is at 295 Kelvin, and if in the compressor the exergy destroyed is change in entropy into m dot. So m dot into S2 minus S1, which is comes out to be 0.01502. So exergy destroyed is nothing but T naught into entropy generated. So 295 into the SGen will come out to be 0.4432 kilowatt. So the next is in condenser. If you do an entropy balance, the entropy generated is nothing but m dot into S3 minus S2 plus Q dot H, which is heat rejected to the ambient, divided by the condenser temperature. So this will give me entropy generated as 0.02138. Similarly, exergy destroyed is T naught into SGen, which is 0.6308. Similarly, in expansion wall is there is no heat transfer, so entropy balance will come out to be change in entropy. So change in entropy into m dot into T naught will give me exergy destroyed. It comes out to be 0.5651 kilowatt. And then in case of evaporator, again the inlet entropy is m dot S1 plus QL by TL minus exit S4, m dot into S4. Doing entropy balance, we can find out the again S generated into T naught, which will come out to be 0.2054 kilowatt. So this is the each of the exergy destroyed components in each of the components. So now the exergy of the heat transfer to the low temperature medium is QL into T naught by TL minus 1. This then it's come out to be 0.6585. So this is also the minimum power input for the cycle. So the second law of efficiency of the cycle is exergy divided by W. So we are converting the Q heat which is getting we are getting from the evaporator, we are converting that into work, so that divided by W, or we can find out the COP by COP, that also can be done. So exergy efficiency will comes out to be 26.3%. So if you see, similarly we can solve this as COP by COP Carnot. So COP Carnot efficiency is TL by TH minus TL. So this comes out to be 8.22, and we saw the previously we calculated COP is 2.16. So second law of efficiency is 2.16 by 8.22, which again comes out to be 26.3%. So now if you see, the total exergy destruction is W divided by exergy which is of the in the evaporator, heat generated in the evaporator. So that comes out to be 1.845 kilowatt. And if you add up each of the exergies destroyed in each of the component, that will also again comes out to be 1.845 kilowatt. So I hope this is clear. So, I've seen VCR system, which we have studied each of the component and how it's affecting the exergy efficiency of the system. So similarly, next week we'll see some problems on psychometrics and air conditioning processes. And thank you.